So we have just finished looking at how to calculate refractive angle light beam passes between two different mediums. The video explaining these notes is on the previous Firefly blog page. We're not going to recover that. If you're unsure on that, you'll need to go back to the Firefly blog and watch those videos again. Today, we're going to be looking further on in the notes, starting on page 6. With a little bit of revision, first of all, if you remember our third year topic of electromagnetic spectrum, you remember that the spectrum ranges from radio waves with long wavelength and low frequency to gamma rays with short wavelength and high frequency. Within this spectrum, we have visible light, the colours of light which we can see with the eye. Each colour has different wavelength or frequency. Red light has the longest wavelength and lowest frequency. Violet has the shortest wavelength and highest frequency. And what we have here is a picture over on the right. If you take white light and shine it into a triangular prism, that prism separates the light out into the corresponding parts of the visible spectrum, ranging from red to violet. So we've got this nice colour diagram here. Usually we would actually do this in class, however, with you being at home, we'll just show you a picture. So white light entering a prism will be separated into its separate colours. Now what that means is that the white light is refracting in the glass, and some of the colours are refracting more than the other colours. Some of them are bending further away from the normal. And this worked example bases itself on that principle. A ray of light enters a tungsten filament. A ray of light from a tungsten filament enters the glass prism as shown below. The refractive index of glass is 1.53 for blue light and 1.51 for red light. So our light is separated into its corresponding colours within the glass inside. Let me just get the highlighter in here. Now, of course, our light then spreads out just like our image over here. So that when it gets to the boundary, it refracts with the glass. If you were to draw your normal in here, you would have that drawn at 90 degrees. So you would have some angle of refraction to here and a greater angle of refraction down to here. Now, the question wants to know what this angle alpha is between our rays Q and P. So I'll just clear that off. So alpha is the angle between Q and P. If P and Q represent the ends of the visible spectrum, which is the blue end. So first thing we need to do is remember our formula. Refractive index is equal to sine theta 1 over sine theta 2. And let's just have a look at the red light. So we know that the refractive index of red light is 1.51. 1.51 is equal to sine 60 divided by the sine of the angle. Where does the 60 come from? We have to add a little line onto our diagram. Okay, we would look with a protractor to draw this at a right angle to the medium. And we can see there that this angle in here is going to be equivalent to 90 subtract 30 degrees, which equals 60 degrees. So our light enters at 60 degrees. Some of it is refracted to give us Q, and some of it is refracted to give us P. We're trying to find the angle between Q and P. So our formula, N2 over N1 equals sine theta 1 over sine theta 2. In this case, we're looking at the refractive index of red is equal to the sine of the angle in air divided by the sine of the angle in glass. So 1.51 is equal to sine 60 over the sine of the angle when it is in the glass. When we rearrange that, we have sine of the angle in glass is equal to sine 60 over 1.51. The inverse sine of that gives us 34.99 degrees. Let's have a look at blue. So the blue light, okay, Again, it is incident at 60 degrees, and then it refracts inside the glass. So the refractive index of blue light is sine theta air over sine theta glass. In case you're wondering, we do not have to include our sine theta 1 just because the value of it is 1. Okay, you could have it like that if you wanted, and you could have this like this if you wanted. However, because we know that it's 1, we don't necessarily have to show it. So from the question, 1.53 is the refractive index of blue light. Use the wrong colour of blue, that's all right. There we go. So 1.53 is sine 60 over sine of the angle in the glass, because that's our material, our medium 2. So the inverse sine of 60 over 1.53 gives us our angle of 34.47 degrees. So what we know now is that this angle in between alpha, okay, there, is equal to the angle of refraction for red, subtract the angle of refraction for blue. Our larger angle subtract our smaller angle. 34.99 subtract 34.47 gives us 0.52 degrees. So that question looks complicated. It isn't too bad. You just have to, first of all, calculate the incident angle by drawing your normal. Work out the refracted angle for each colour, red and blue, and then take away the two angles you've calculated to find the difference between them. The next part of the notes is theoretical derivation of other formulae that is in the course for refractive index. However, being able to derive these formulas or knowing how they are derived is not in the course. I'm going to post a separate video on how you would derive these. You do not have to watch it. It is up to yourself. If you're interested in the maths behind the formulas, you can do so. We are going to skip forward to the formulas themselves, which we are interested in our summary box. And because it's important, we're going to say to know all of our formulas that we use when we have light entering one medium from another, summarised nicely for you on page 9. So if you have a material and you have a boundary, you have material 1, material 2. When light goes from material 1 into material 2, you can work out the angles involved by using n2 equals over n1 equals sine theta 1 over sine theta 2. If you wanted to work out the speed of the light in these materials, you would also be able to use n2 equal over n1 equals v1 over v2. And if you wanted to work out the wavelength of the light when it changes mediums into different materials, that is n2 equals lambda 1 over lambda 2. You can put all of these together, and n2 over n1 equals v1 over v2 equals lambda 1 over lambda 2 equals sine theta 1 over sine theta 2. So you do not need to necessarily know how to derive these. It is not part of the course, but you will be asked to use the formulas on this page. Snell's law, the refractive index and speed, and the refractive index and wavelength. And that is what the majority of this period today will be. It will be your chance to practice using these formulas in the question booklet. Question 1 and question 2, I have posted solutions to these onto the Firefly blog. They're also here in OneNote. Question 3, 4, 5 is what we're going to have a look at today. Solutions are also now in OneNote. I was able to upload those, so you can check them as you go. However, let's have a look at this worked example before you get a chance to do these on your own. Note that when light is refracted, the frequency does not change. This is important. The frequency which the light is being emitted from its source is not affected by the changing medium. Okay, the frequency of light remains constant. The speed does change if it enters a different medium, and the wavelength will change correspondingly to the speed. Remember our formula, lambda equals v over f, and our frequency is constant. So if speed changes, then lambda will also change just by looking at that equation. So here we have some wave fronts, and they are entering a boundary. Once they have entered the boundary, let's say this is our boundary here, they have changed direction and the wavelength has changed. The spacing between each wave is now less. Okay, and we're going to have a look at some example here, which is typical to the question you might expect to see in a test. So a beam of monochromatic light of frequency 4.85 times 10 to the 14 hertz passes from air into liquid paraffin. So it's going from air into paraffin. Air giving us N1, paraffin giving us N2. Calculate the refractive index of the liquid paraffin. We are told that the speed of this light in the paraffin is 2 times 10 to the 8 meters per second. We already know that the speed of light in air is 3 times 10 to the 8, so we can write down some of the information that we know just to help us completing the equation. The speed given to us is 2 times 10 to the 8 meters per second. So it's traveling slower in the paraffin than it is in air. Frequency is 4.85 times 10 to the 14 hertz. Calculate the refractive index. Okay, we can use our formula for refractive index and speed. N2 over N1 equals V1 over V2. So N2 over N1 equals V1 over V2. We know the refractive index of air is 1. So what we have therefore is that N2 equals 3 times 10 to the 8 divided by 2 times 10 to the 8, which gives us 1.43 as our refractive index. So quite straightforward. Identify the numbers from the problem, put them into the equation, calculate refractive index. The last part of the question, what is the frequency of the light when it enters the paraffin? Remember, frequency remains constant. So you should now go back to the question booklet and have a look at questions 3, A, B, C, and D, 4, A, B, and C, and 5, A, B, and C. I'll be online during the period to answer any queries that you may have. Thanks.